Assalamu alaikum and greetings. Here we are in our new video and task. Our assignment once again is to calculate our magnetic flux density at this point A. But also the second part of our task is to determine the current which is necessary to flow through this conductor, but if it was not bent. So we will imagine this, that we have only straight conductor and that we need to determine this current so that magnetic field with this conductor be the same as with the bending of this conductor. We will do that in the second part of our assignment. Firstly, once again, Biot Savart law, B equals mu 0 I over 4 P d, where d is distance, sinus phi2 minus sinus phi1. So what will we do? Okay, we have bended conductor. We will make few different cases. This will be our first case. We will analyze only this conductor, which is infinitely long. Also this one is. This will be our second case. This will be third case. This will be fourth case, and this will be fifth case. For every case we will determine vector for that. Here we have been given a coordinate system, but if you look at carefully, you will see now if it's presented shown like this, this means that the z-axis is positive at not to you, but from you to the table. This is the positive direction of the axis. So every field that has this direction will have a positive unit vector in z-axis, and that is an opposite direction towards you, it will have a negative unit vector of z-axis. So let's firstly solve this case first. What will we have? Okay, this is the conductor, infinitely long. We have a current I. Okay. But our point is here. Look at this. So we have some distance. This is our point A. And we need to calculate a magnetic field at this point. Now this is unusual. We didn't have this case, but we did explain in our first video where I explained Biot Savart's law how to solve this problem. So once again, first thing, or one of the first things that you need to do is to draw this D, which presents distance from the conductor, but in a way that this distance must be normal to a conductor. So here our conductor is ending here, or beginning, but we will say ending. So in order to be a normal, we will have to imagine that this is our conductor. It does not end here, but it goes further, so this is the right angle here. So I will draw. So this is the right angle. But now we need to find our angles. The first angle is when this point connect to the beginning of a conductor. You can see that this is where the current starts, so this is the beginning of conductor. So the angle is not from here to here. It is from this distance, which is normal to a conductor, to the end of conductor. So this is our angle, and always is from this distance, which is normal to a conductor, to the beginning of the conductor or to one end of a conductor. So the second angle we get when we this point connect to the other end of a conductor. This is first end, this is second end of a conductor. And once again, this angle second is from its normal, it is the same normal, to this end. So this is one angle, this is second angle. Which angle is first? The current direction determines it, and we can see that it comes firstly to this angle, so this is phi1, and this is the second angle, phi2. Next, what we need to determine is magnetic field direction. Okay, we have our conductor, this with the current in this direction. We use right hand rule, we close our fingers, and we can see that on this side where we need to calculate it, magnetic field goes from you to the table. So it has this direction. This is our B1, which means it has a direction, is directed in the positive direction of the axis. So it is that B1 equals its intensity times unit vector K plus, because it has the same direction as the x. Okay, now we need to calculate some distances. So firstly we need to calculate this D. This is my B. Okay, what its distance? Let's go back to this picture. So this is my conductor and this is my point A, and I'm asking what's the distance here. That is the same as this distance. So if I put a normal, I will get this distance. Because these are diagonals, that my point is at the center of here, this means that this is B and a half of length of this side. So D equals B and a half. The next, what I need to know to determine is these angles, phi1, phi2. Phi1, because it is infinitely long conductor, so this angle is 19 degrees, phi and a half. Is it positive or negative? We see for angle phi1, the current enters this normal of this angle, enters, so it is a negative angle. But now we need to find phi2 angle. How can we find phi2 angle? Using law of geometry, trigonometry that we know. So one way is we are looking where do we have right triangle with 90 degrees triangle. Okay, we have it here, and we already know this side of a triangle. If I know any other side that could be hypotenuse, discarded, I can calculate every angle of it. But you can see, what is this? Okay, this is my conductor here. This is my point A. Also, because this is a diagonal, I have been given this is side A, this is B, B. So because it is a diagonal center of this means this is A and a half. Now, when I have both sides, I can calculate angle. I can go and calculate the hypotenuse, and then use sine or cosine to find this angle, or I can use tangents, and tangents of angle phi2 is, because it is sine over cosine, hypotenuse will divided will be equal. So we are left sine, and sine of this angle is opposite. So opposite is a and a half. And cosine is equal the adjacent side of a triangle over hypotenuse. So this means this side. So the tangents is opposite side of a opposite side over adjacent side of a triangle. But let me find this up. Because I'm not given the values of A and B. If I have been given the values, what could I do? I could calculate tangents, and I could calculate what is that angle and put it in here. I don't have values for A and B, so I cannot calculate it. Because of that, I will use sine of this angle, using sine trigonometry rules for sine in order to find this angle. In order to find sine or cosine, I must have hypotenuse. So I will find hypotenuse. This is my hypotenuse. Let's say it's R. And the hypotenuse is equal square root of 1 cutted on square plus the other cutted square, which means R I don't think anything else. So now I can use that sine of this angle is the opposite cutted, which is a and a half. So sine phi2 is equal a and a half over hypotenuse, which is this. And very important is to take in consideration, is this a positive or negative angle? Will it be a positive or negative value? But here, in all previous assignments, what we had, and someone can say, okay, angle phi1 is always negative, angle phi2 is always positive. But in this case, that's not correct. So, in this case, once again, the same rule is we must use the same rule. So, where is angle phi2? Angle phi2 is here. And what happens? Does the current comes in or comes out of the normal of angle phi2? His normal is here. So, you can see that the current for this angle also, like it did for phi1, enters. So, it is a minus. We must take a minus in consideration. So sine 2 is a minus of this value. Well, how can we a little bit make it simpler? Here we have a squared over 2 square plus b square over 2 square. We have common, and we can draw it in front. So what will we have here? We will have a square plus b square over root, and here we will have a root of this, root of a square plus b square over divided with the root of 2 square, which is only 2. And we can divide one inner, one outer part of so we get this. Now this is equal a times this. And we put everything here. So our B, magnetic flux density first, will be equal μ0 I 4P times D is B and a half times sinus phi2, which is minus A over A squared plus B squared. Sinus phi1 is a negative, so that is a minus sinus, and this minus will give plus, and sinus of 90 degrees is 1. So we get this, that this is equal μ0 I over 2p v1 minus A over if we want to write this as a vector, so we would here add vector and here k times k. Now let's calculate for the second case. The second case is this case. So I have this. The length of this is B. I have a point here where I need to calculate our magnetic field. So what I firstly do, I have the current here in this direction. I firstly draw the distance, so it is a normal to my conductor. Then I connect this point to the beginning of a conductor and this point, the same point, to the end of a conductor, and I got two angles. What are these angles? Well, firstly, I need to know what is the distance. The distance, so once again, is a and a half. So, what is this? Is because this is B, so this is B and a half. The next thing we need to know is the direction of our magnetic field. So we will use the same right hand rule. Okay, we have our conductor, we have the current, and we can see that on this side the magnetic field is directed to you, goes to you. So this is our B2. Once again, what is the first angle? Okay, I have two angles, which is the first? The current direction determines it. It comes firstly on this angle, so this is Phi1, this is Phi2 angle. How can I find the first and second angle? Now that is a small problem, but it is solved the same way as here. How will we solve it? Okay, what do we know? We know that this side is A1/2, that this side is B1/2, and we need to know this and this angle. In order to know these angles, you can use also tangents. So we need to find sinus Phi1. It is for right triangle. This is sinus Phi1. It is equal to the opposite side, which is B1/2, through hypotenuse, which is square, A square plus B square, over 2. We can short these two. So we can get that this is B over A square plus B square. But very important thing is to determine, is it a positive or negative? Well, if the current, we can see P1, it's normal, the current enters, so it means it's a negative value. Minus. Sinus Phi2, the same way, sinus Phi2, so this is Phi2. Also, it is an opposite, which is B1/2, divided with hypotenuse, which is square plus B square over 2, which means it is B over both are the same angle, and we enter this sinus Phi2 here, it's normal, and we can see that current comes out of its normal, so it is a positive sign. When we put this minus here, it will become positive, so our resultant magnetic field B2 is equal mu0 I for E T. D is the distance from our conductor, which is A1/2, and this 4 we can divide it, so we can get this times, it will be this plus this, which is equal to the 2 times of this. So B2 equals mu0 I BA times B over. If we want to write it as a vector, very important thing, look at here, what is the direction of B2? The direction is towards you, but the positive direction of z-axis is from you to the table. So this direction is opposite to the positive, which means if we write this as a vector, it is minus unit vector. And this is times. Now, also, for us, it's very important to see, to conclude, you can conclude right away or after. Look at this. This conductor has the same length, has the same distance from this point where we need to calculate it. So, let's see, does it have a same direction? Which means the identity of this which creates this part of a conductor of a magnetic flux density is the same. But let's just check the direction. Using right hand rule, we can see that here it has this direction. It has the same direction as B2. So B4 has the same direction as B2 because it has the same current, because it has the same length, because it has the same distance from this point. They are equal. So the B2 is equal to B4. Now let's third case calculate and find so our third case is this. I have a conductor. Here is the point. This is my current direction, I. This is my point A. So I need firstly to draw a distance which is normal to this under 90 degrees. Then I will need to connect this point to the beginning of a conductor and this point to the end of a conductor, and once again I found the two angles. So this is which is the first angle. This is the first angle while current flows on which it comes on. So this is phi1, this is phi2. What is the distance? This distance, we look at the original picture, so it is b and a half, as you can see. B and a half. This part, this complete conductor is length of A, so this is A and a half, so it's this A and a half. And using the same method, same analogy, we can calculate everything. So, firstly, because we need to find angles sine phi2 and phi1, we will firstly find hypotenuse. Hypotenuse is once again the same, so it is a square plus b square over 2. This is first cateted b and a half, second cateted, and you calculate it like in previous ways. So sinus phi1, firstly let's see is it a positive or negative, because the current enters this normal, it has a negative value, so it is minus its opposite side is a and a half divided with the hypotenuse. So sine phi1 equals minus a phi1. Now sinus phi2, this is the second angle. Let's see it is positive negative. The current comes out from its normal, so it is a positive angle, and it says that its opposite side is a and a half divided with the hypotenuse, which means both angles are the same. We will get this a squared. This minus and this minus will give us a plus. We have that d is equal b and a half, so we will get that b3 is equal mu0 I. For this 4, and because d is b and a half, we can divide them. Also this plus this, because it will be the same, will be 2 times that, and divided with 2 that's left here is 1. So the result is B times B times A over A squared plus B squared. And if we want to write it as a vector, let's determine its direction. So we use the same right hand rule, and we can see that on this side it comes from the table to you. So this is vector B3. It has an opposite direction than our positive z component, so it is minus k. Oh, dear Lord. And we have another case to calculate. We already determined that this creates the same magnetic field density as in case 2. And only one case is left. It is this case, so it is similar to the first case. Okay, we have the conductor which begins here and ends in the infinity. We have the current I. So this is our fifth case. Somewhere here is our point A. So first thing we always say that you need to do is, from the respect I'm saying we, even though it's me, we need to draw a distance. We already told you that that distance needs to be normal to a conductor. Our conductor is here, but we will imagine that we will extend it. So this is a normal. Distance d, this is distance. This distance is actually this distance, so we divide this side with halves. So it is b and half b. Then, how do we find the angles? We connect this point with the beginning of a conductor and this same point with the end of a conductor. Which is the first angle? So first angle is this, normal to the beginning of a conductor, because this is the direction of current. This is the first angle that it comes up. And the second angle is also must be from this normal to the end of the conductor. So this is that. This is the second angle. We need to determine the direction of magnetic flux density or magnetic field, same right hand rule. We can see that on this side the magnetic field goes into the table, on this side goes from the table to you, so it has this direction. Which means it is in a positive direction of the x. Now, other thing, okay, what is this distance? This distance, okay, we come back here, so this is the beginning, this is my point A, so this distance is actually this here. So it is A and a half. Half of A. And also we can see from here that phi 2, this angle is because it is an infinitely long conductor, this angle is 19 degrees, but we must check, is it a positive or negative angle? This is because the current comes out of its normal. This is the normal of angle phi2. It comes out, it has a positive value. But angle phi1, we don't know what its value, so we will determine it, calculate it. In order to calculate sine of this, okay, we have this cathode of our right triangle. Here it is. We need hypotenuse because we have both catheters. Hypotenuse will have the same value as previously, which is divided with 2. So my sine phi1 is equal. Firstly, let's determine is it a positive or negative, because in our previous videos, once again, we had phi1 is negative, phi1 is negative. But look at this case, where it's normal from the angle phi1, it's here. Does the current comes out or enters? It comes out from its normal, so it is a positive angle. So sinus phi1 is a positive angle, and it is equal to the opposite side of this right triangle, opposite cathode, which is a½ divided with when we enter this in this equation, what will we get? Sinus phi2 sinus 19 degree is 1 minus, because sinus phi doesn't change, is a positive value, it means it will be minus this. So this is our B5 is equal to 0 I. D in this case is B½ so it will be 2PB times 1 minus A over square. Let's check. If we want to write it as a vector, we can see its direction is in the same direction as a positive part of the axis, so it is plus k. And now, simply, our resultant magnetic field at this point, B is equal to B1 plus B2. It will be B2 plus B3 plus B4, but B2 and B4 are the same, so I will write it as this 2 times B2 plus B3 plus B5. We have calculated all of them, so the end result will be, and I will write it here, so B resultant is equal in the direction, and the unit is Tesla. Please remember that. But now let's analyze the second part. The second part says, okay, let me have the same conductor but without bending. So it is at the same distance. Okay, this point is at the same distance. It is B and a half. infinitely long, and only straight. And I have a current I, and it wants, but this is the second case, we will note it as B case, so we will note this as B current index, the current of the second case. So we need to determine which current is necessary in order that this field be equal to this field when our conductor is dented. So we will very easily find magnetic field of this conductor. We already have magnetic field of this conductor. We will equal them. So for this case, using Biot-Savart's law, for B case, we will say it is mu0 I over 4p times d, distance is b and a half, times sinus phi 2 because it is an infinitely long conductor. This is phi 2, this is phi 1. These angles are 19 degrees. This will be, phi 1 will be negative, phi 2 will be positive. So it is like this. So our B four divided with 2, we will also have here 2, and we can divide it with the rest of 2, so we get, this is identity of our, and I will only here put B because it is the current of this B case. Of the second case, you can write whatever you want, note it whatever you want. So my assignment tells us determine this current in order that magnetic field be the same. Okay, I will simply, this must be equal to this, so minus